about this, and it's a pleasure to do it. And about 2/3 of you are tired of seeing my ninja introduction to the population protocol model, but there is always some people who haven't listened to it, so that we have to do it again. So you can go to sleep. I think more or less most people who haven't heard it, I think, are on this side for some reason. So anyway, so what are population protocols? And I always like to introduce them by an example. So there is this society of warriors, the Deaf Black Ninjas Society, and it is a secret society of warriors that is so secret that they don't know each other and they don't know how many they are even. Now and then they get a message from the leader of the society asking them to meet somewhere to do something, and that's just what has happened. The leader has asked them to meet at the Zen Garden in the dark in order to attack a castle. But they only attack if at least 100 of them show up, right? Not always the ninjas show up. Some have been wounded, others are under magic spells, others have tax forms to fill, and so it's not always 100. And the problem is that when they arrive in the castle, this is what they see, and they are all deaf, they don't hear anything. So the problem is how can they find out whether they are 100? So how will you do it? And usually when people are confronted with this problem, their first reaction is to say, well, that they don't seem to be able to communicate, there cannot be a solution. But then you forget that ninjas are mobile, and then they have the opportunity to communicate. Actually, what the instructions that the sensei has given them is to just, when they arrive in the garden, they should just wander around. Okay, actually, I think I have it in the slide, right? They should start wandering around. And of course, eventually, two ninjas will bump into each other, and then they can communicate. And now I have, is it okay? Can you still hear me on top of the, okay, because it's not so easy, I have to. Good, so then what should they do when they bump into each other? Well, it's easy. So the idea is that the sensei, the leader of the society, we usually call him the sensei, they have been told to carry a pouch. And to come to the garden with the pouch, one pedal in it. And then when two ninjas bump into each other, one of them gives all the pedals to the other. Okay? And then, even at this point, you can already think what's going to happen. What's going to happen is, since they are moving randomly, eventually some guy is going to collect all pedals. Okay? And then at that moment, that guy the guy doesn't know that she has collected all pedals. Okay? But that will happen eventually. But what you can tell the guys is, whenever you have 100 pedals in your pouch, well, you already know that there are at least 100 ninjas. And then whenever you interact with somebody else, you tell other people. Okay? So that's the idea of the protocol. So if there are at least 100 ninjas, some ninja eventually collects at least 100 pedals, knows there are at least 100 ninjas, and the ninjas who know, they can spread the word. So this is let's visualize the protocol for, instead of 100, 4 ninjas. And imagine 5 ninjas have shown up, and how is the protocol going to run? Well, each ninja is in a state, the possible states are 0 to 4, corresponding to the number of pedals in their pouch. Initially, they are all in state 1, because they have 1 pedal in their pouch. And then, these are the transitions that tell you that when if two ninjas with M and N pedals interact, then one of them gives all the pedals to the other. Okay? So for example, these two ninjas interact, and then this one collects the 2 pedals, this one has 0. If these two ninjas interact, nothing changes. If these two ninjas interact, then also again the result is 2-0. And then when these two ninjas interact, what happens then? Well, then the joint number of pedals is 4, and then both know that at that moment that they are at least 4. So we can simulate this by saying that both of them put 4 pedals in their pouch, right? And from that moment on, whenever two ninjas interact and one of them has 4 pedals, it tells the other, yeah, we are already 4, and then this propagates, and now they have reached a situation where everybody knows we are at least 4, and we can attack. Good. This we represent like this. So the idea is that you will see it in a moment more clearly. So the idea is that this state 4 is labeled with an opinion. With the opinion, everything is fine, thumbs up, right? and then they have all reached consensus that what we should do is, the consensus opinion is thumbs up. Good, and until then they were thumbs down, right? As long as they didn't know they were for, it was thumbs down. Good, so this is a brief introduction to the model. It was presented about, by now 20 years ago by Anglois, the same person that who introduced the L-star algorithm, and some other colleagues from Yale. And they introduced this as a formal model to describe, swarms of mobile agents, which interact randomly in pairs with a goal. And the goal is to decide some property of their initial configuration. In this case, a very simple property, R is the number of agents at least 4. So, so for example, does the initial configuration contains at least 100 agents? But there could be other properties like initially they could be in 2 different states, and the question is whether there are more agents in one state than in the other. So, and this started, you have seen the switch, right? Swarms of mobile agents. So one has to think of one can think they were thinking of little sensors or so, which are, a tiny application in your mobile phone, and during the pandemic, right? During the pandemic, we had these applications where in our phones where 2 people would come close to each other, and then your phone would silently change state because of that. Good. So, but then what happens is that a few years later, since the late 70s, they were also suggested as a model of natural computation, where you have to look at the agents as atoms or molecules, okay? And in particular, there is a model called chemical reaction networks, which is very close to the population protocol model. And the idea is to look at a chemical reaction like this, from school, as an interaction between 3 molecules here, 3 agents, right? One agent is in a state CH4, 2 agents are in a state O2, and these agents can change their states into 1 agent CO2 and 2 agents H2O. The model is a little bit different because sometimes there will be more molecules on the right than on the left, and then this can change or cannot change the model significantly depending on different semantics, but let's not get into that for the moment. So these are the 2 slides I have for how important it is, NSF expedition in computing and this, but for this audience this is completely irrelevant. You don't need my answer, right? You don't care, you couldn't care less. So let's move to the formal description of the model. So you have a set of states. I illustrated with the protocol we have just described, right? There are 5 states in our example. And we have each state has associated an opinion, and there are only 2 opinions, thumbs up, thumbs down. In our example, all these states are thumbs down. This one is thumbs up. There is a set of initial states. In our case, only this state. All agents are in this state initially. And there are transitions. This is a sample of possible transitions, right? Not all of them. For example, 2-1 goes to 3-0, or 1-3 goes to 4. Good. Then we introduce the notion of configurations. The configuration is just a mapping assigning to each state the number of agents in that state. Agents are indistinguishable. We only need to know in which state they are. And the notion of initial configuration, which are the configurations in which all agents are in initial states. In this case, there is only 1. In general, there could be 7 of them. And then, so the initial configuration is just a vector. And what the agents want to decide is some property of this vector. And then a specific population protocol has a goal of deciding a property of the vector. And it should work for all vectors. Okay? And so what is the semantics is clear for each initial configuration. For example, this one. Imagine you have initially 4 ninjas. This is your initial configuration. Okay? And then this is the reachability graph. So from 1, 1, 1, 1, for example, you can go to 0, 2, 1, 1. And from 0 to 1, 1, there are 3 possibilities. For example, if two ninjas, these two ninjas interact, 1, 1, then they will go to 2, 0, and then you go here. Or if 2, 1 interact, then they go to 3, 0. Or if, for example, 2, 0 interacts, they go to themselves. Now, at this point, of course, you are all thinking buses, and this is, in a moment, we will see the correspondence to buses. There is something now that differentiates the two models, namely that we introduce probabilities. Because, oh sorry, this is one too far, because what you do is assume a semantics where at each step you pick two agents independently at random and let them interact. Okay? Then, for example, which is the probability of moving from here to there, is only 1/6, because the only pair that will take you from here to there is 1, 1. There are 6 pairs, and the only pair is this one, so it's 1/6. But from here to there, the probability is 1/3, because two could interact, these two could interact, this pair or that other pair, right? So there are 2 pairs where they could, which could interact. This and this, or the 2 and this. Good. And the other, in all other 3 cases, they stay here. So then you assign these probabilities, and this means that for every initial configuration, you have a finite state Markov chain. Good. So then you define, as usual, the notion of infinite runs in a Markov chain. You assume always you design it so that all runs are infinite. Okay? And in this particular case, you can see that for this configuration, eventually, with probability 1, the agents will land here. Okay? So the idea is that when they are here with probability 1, they will eventually land there, and this is a configuration where they all agree to thumbs up, and they will stay there forever. Good. So now you can define, we can formally define, when does a protocol decide a predicate? A predicate goes from the set of initial configurations into 0, 1. Actually, I should have been less lazy and replaced 0 and 1 by thumbs up and thumbs down. Well, 1 thumbs up, 0 thumbs down. And what you say is, well, for every initial configuration, the initial configurations are inputs, right? Are the inputs to the computing device. And for every initial configuration, the runs starting at that configuration should reach a stable consensus. And what is a stable consensus? Is a configuration where all agents agree, and such that the same happens, the same holds for every configuration reachable from that configuration. So the agents have reached an agreement, and they will never change it. Okay? It's not only, in this case, it's not only that they can only change it with probability 0, it is that they will never change. It's impossible to reach a configuration which is not a consensus of the same kind. So, for example, this is trying to visualize here what happens when, or how does the semantics of a protocol look like, which decides a certain predicate phi. So, when you start with a configuration C0, and that gives you a finite state Markov chain. So the configurations reachable from C0, which can look like this. It's going to have bottom strongly connected components, and the protocol with finite probability is going to land here eventually, and with the 1 minus that probability is going to land eventually here, right? So actually what has to happen is that these 2 blobs, these 2 strongly connected components, should all be configurations of consensus 0. Okay? Because that means these are stable consensuses and of the same type. For example, if there would be here one configuration which is not a 0 consensus, then the protocol is ill-designed. The protocol does not work, because with positive probability, it can give you 2 different answers, okay, for the same initial configuration. So in this case, then, all agents agree to thumbs down. Here, all agents agree to thumbs up. Here, all agents agree to thumbs down. And it should continue like this for all possible initial configurations. And of course, whether it's up or down, should correspond to the definition of phi. Everybody happy? Good. So the protocol I have given you is a protocol that decides the predicate x bigger than or equal to 4, where x is going to be the number of agents, okay? Good. So of course the analogy, everybody, you will know, you will see the analogy. A state of a population protocol is a place of a Petri net, and to confound people who like vector addition systems with the states, it's a counter. Sorry, but the guys in population protocols, they call it a state, yeah? They were not there to just please you and call it counter. I'm sorry. So they call it counter, and notice that the population protocol is going to be a one-state bus. So the interaction, transition line is going to be, in Petri net terms, a transition with 2 input places and 2 output places. Well, these 2 places could be the same, and then what you have is one single input place, but with weight, with an arc weight 2. And in a one-state bus, what you are going to have is a self-loop, okay, which decreases 2 counters, increases 2 counters. And the population protocol scheme that is without an initial configuration is going to give you a net without a marking, or the one-state bus. And then when you a configuration corresponds to a marking in Petri net or to a configuration of a one-state bus. And the population protocol then is a Petri net, very special kind of Petri net where all transitions preserve the number of tokens, right? But an infinite family of initial markers. Good. And in the one-state bus, you will have one infinite family of initial configurations. Good. So now look at this the protocol we have seen, and you can of course construct it for any constant c, whether it's 100 or 4 or whatever. And how many states do we have? We have the states 0, 1, 2 up to c. Now that means this is, if you look at the number of bits you need to describe this predicate, the number of states is exponential in the size of the predicate. Okay? Good. And the question is whether we can do better or not. And this is the question about the search for succinct protocol. Succinct means with as few states as possible. Now the question is, and then we define the state complexity, right? The state complexity of a predicate is the minimal number of states of a protocol that decides the predicate. Good. Now, surprisingly, I am going to give you some motivation for this. Why do we care? Well, there is a very natural answer to that. So, as people are mostly interested these days on population protocols as a model for natural computing, for this, when they look at them as so similar to chemical reaction networks, right? And in that case, an agent is a molecule, and a state, and this is the important thing to keep in mind, what is a state? A state is the species of the molecule. So CO2, H2O, or whatever, okay? So if you want to implement in vitro a protocol with 10 states, you are going to need 10 different chemical species, and you are going to be, as a chemist, you have to, the word is not chemist, right? I don't know, how do you call it? Anyway, you have to find reactions which correspond to it. Okay, so, and now, so the transition, which is a chemical reaction, is going to be something like this. Here, 3 molecules go to these 3. You could say population protocols only deal with reactions with 2 constituents and 2 here. Don't worry about that. Things like this could be simulated. And in fact, from a really physical point of view, what happens in reality for a reaction like this is a sequence of reactions with at most 2 interacting, right? So in fact, this is an abstraction of what happens in reality. In reality, what happens is the population protocol model. Anyway, so and now imagine, right, that if we have a protocol for x bigger than equal to c that we can implement in vitro, then we might be able to implement in vitro something like this. So you have here a chemical soup. Here are your molecules, right? And now you start adding molecules, very few of them if you want, so one at a time. And then what happens is that at some point it's going to change color. because the molecules themselves are going to identify, oh yeah, we have exceeded the threshold, now we are enough, and then you can use that in order to change the chemical composition so that, for example, it gets a different color. So now if you want to do science fiction, you can think of trying to use this basic math in the future, right, in order to have, for example, solutions in your body which identify the concentration themselves and regulate themselves. You know, you can dream. People in quantum computing are doing exactly the same, right? They are dreaming. Most of what you hear when you read in the newspapers are dreams, not about quantum computing. So, so this is the dream. But now, what happens? So, the color should change when the number of molecules reaches this constant C. So we need to implement a protocol for x bigger than or equal to C. And what is C for this? So, the Avogadro's number is 6 times 10 to the 23. How many people here remember what the Avogadro number is? You don't? I should, Okay, it's the number of molecules in a mole of a substance, right? So basically, it's the ratio between microscopic and macroscopic. So if you want to have a macroscopic quantity of some chemical substance, you need around this number of molecules, something like that. Okay? So actually, we are going to need a protocol for C, where C is about 2 to the 60. Okay? And this means it's not difficult to get 2 to the 60 molecules. That's not the problem. The problem is to get 2 to the 60 species. Where are you going to get 2 to the 60 species, right? 2 to the 60 different kinds of molecules and chemical reactions for that. That's going to be more tricky, right? So that's the motivation for trying to do better. So it's very different from the situation when you are thinking of artificial devices. It's very easy to get a tiny silicon device with 2 to the 60 states. Right. Because you need just 60 bits, right? But it's very difficult when you want to implement it in a natural model. Okay, so now the question is, can we do better? Let me change the C, just for simplicity, it doesn't have any important consequence, to a power of 2, right? So then we have 2 to the k plus 1 states. Well, we can do exponentially better, and it's a little exercise. Maybe somebody here comes up with a different protocol. What's the idea? Maybe somebody comes up with that. Okay, yeah?
You store as a log, and you only add up if you have equal numbers.
Great, full points, okay? So you just, your states are now only the powers of 2 plus the 0. Okay, initially all agents are in state 1, but now only equal powers react with each other. Let me just mention something to you. If you think about this for a little moment, you will see, of course, this is much better. I only now need much fewer chemical substances, but I am paying a price. It's much slower. Because now most of the interactions do not produce anything. And then we are not worrying about that for the moment. We are just, it's already difficult enough to know which is the bound on the number of states. But it's only the beginning of a large, the final goal, of course, is there any formal model which is powerful enough, can model a large variety of predicates, and for which we can have reasonable implementations in the sense of reasonable number of states, reasonable speed. But okay, put that aside for a moment. As I said, the restriction to 2 to the k is completely irrelevant. It takes a little bit of work, but you can achieve the same logarithmic number of, linear number of states in the number of bits of the constant, right, for any number. Okay, and now, can we do better? So, can we go to log C? The second trivial exercise, but a trivial exercise that Mikhail, Stefan Jackson, myself managed to publish. It was of course not the only result of the paper, but it is published, so we give it a reference. it's clear that you cannot achieve this for every C. And why is this a little exercise? Because, okay, instead of thinking what is the minimal number of states that I need in order to achieve a constant C, let's think the other way around. I give you a budget, I tell you, I give you 10 states. And then the question is, which is the largest C for which you can find the protocol? Okay? Well, that is definitely bounded, I mean, or let's say, which is the largest C such that you can find protocols for all numbers up to C. Okay, that's definitely bounded by the number of protocols that you can have with C state, sorry, with this budget at the states, and that's exponential in the number of states, right? And it's very easy. So this means that the constant that you can achieve so that you can really find protocols for up to that is going to be at most logarithmic. Okay? So that tells you that you cannot do that for every C, because otherwise you don't, basically you don't have enough protocols to achieve it. Good. So, but the question is whether you can do it for infinitely many C. And you know, the point that originated all this work was that the result, which is probably relatively well known to many of you, immediately tells you that it works for infinitely many C. Although under the, by adding a feature, which is by allowing compilation protocol with leaders. Well, before going into that, let me tell you what is a leader. So the idea is that a leader is an agent. Let me just give you an example of a protocol with a leader. I am going to give you a protocol with a leader for this predicate, x equals 1. So initially ninjas are blue or red, and the question is whether is there the same number of blue and red ninjas? Well, and the idea is that the ninjas have a helper, which is usually called the leader. That is a person, is an auxiliary guy who is not part of the input. Okay? And the leader is going to do the following. The leader is initially in a state where, okay, I haven't seen any ninja, so I assume it's the same number. And then if the agent meets a blue ninja, then it goes to the state, okay, I know that there is at least one blue ninja. And then from that moment it searches for a red ninja. It is going to only to interact with the rest if there is a search, it's only going to interact again with the red ninjas. Okay, if it finds a red ninja, it goes back to the state, okay, same number. If it finds now a red, then it says, okay, one more red than blue, and so on, right? And all the ninjas it meets, they go passive. They are not involved in the computation anymore, right? So the idea is that eventually the leader is going to have the side, is going to take the side of the majority and stay there forever. And basically, whenever the leader meets anybody, it communicates the current result. It says, for the moment I am blue, for the moment I am in a tie, for the moment I am in red, okay? And, you know, if there is a tie, then the leader from some moment on will always be in the tie state, and it will communicate it to everybody, and everybody will reach that state and stay there forever. Okay, so that's the idea of the protocol. So the leader stays, the leader has 3 states. The leader is flying from ninja to ninja, interacting with the ninjas, right? The ninja states are initially the initial states, and then the states where, okay, the leader has told me that the answer is blue, the leader has told me the answer is red, there is a majority of red, the leader has told me that there is a tie. These will be thumbs up, they will be thumbs down. So, and then you will have transitions like this, for example. And in this particular case, it's only the leader which interacts with the rest, but that doesn't have to be the case in general. Okay, formally we are thinking in terms of buses. What is a protocol with leaders? Because there could also be more than one leader. The protocol with leaders is a protocol that assigns to an input. You know, in this case, the input is number of blue ninjas, let's call it B, and number of red ninjas, let's call it red. In the population protocol without leaders, this input is assigned an initial configuration where only 2 states are carry agents, right? So there are two states. If you go in terms of Petri nets, there are going to be two places, one with B tokens, one with R tokens. In the case of a population protocol with leaders, the initial configuration is this plus a fixed configuration independent of the input. Okay? So that's the difference. So in this case, in the case of a population protocol with leaders, you have a sort of affine mapping between input and initial configuration. Everybody happy with that? Good. So the number of leaders, the important thing is the number of leaders is independent of the number of agents. Good. So how can we then prove that for infinitely many numbers C, there is a protocol with a leader and log C states that computes this? And this is a direct consequence, as I said, as I announced, of a result that many of you are familiar with. And that was the first point where we saw, oh, Petri net theory or the theory of VAS has something to say here. It offers you a direct answer to a question that people in the population protocol area maybe are interested in. And the result is a result by Maya and Meyer, goes back to about 40 years, right? And so you are probably all familiar with the construction that, you know, it is the construction, in order, Lipton's construction to prove that the covariability problem is in X space, right? And basically what you do is simulate the counter machine, but weakly simulate the counter machine, and then what you know is that the counter can go from a state to another state only if the value of some counter is bigger than a double exponential number in the number of states. Good. Then this construction was given by Lipton in the 70s, and then some time later, Meyer and Meyer improved it by saying, well, it also works if the VAS is reversible. Where reversible means that for every transition, there is a transition in the other direction. Okay? So probably everybody happy with that, right? Mm. So then a bit more precisely, we can say there is, for every n, there is going to be a reversible VAS of linear size and two distinguished states, S and T. This is a vector addition system with states, if you want, such that the shortest firing sequence leading from S to T has length like this. And when I say leading from S to T, I say from a configuration with S to a configuration with T, and I don't care about the values of the counters. Okay? Good. Now, of course, there is also a way back, because this is a reversible one, right? So if you can go from S to T, you can also go from T to S. So everything here can be reversed, but this is going to be, so wait a second, let me see, yeah. We can then immediately construct a reversible protocol. It's not the protocol yet that is going to decide the predicates, right? Not yet. But it is a reversible protocol that we construct like this. We are going to have a leader whose states are the states of the vector addition system with the states, okay? And there's going to be only one agent there, right? And the states of the leader, it's going to be one ninja, if you want. I should have done a bird. And it's going to have two special states, one where the ninja is red and one where the ninja is green. The leader changes colors when it moves from state to state. Now there is going to be another initial state, which is the initial state of the normal agents, not the leaders, the ones that they input, right? And then the idea is that by constructing the VAS, the leader may move from red to green if and only if the number of yellow is at least 2 to the 2 green, right? Well, now notice that the leader may move from here to there or not, but the idea is that the leader, whenever it goes somewhere, it will eventually go back to here, because it's reversible, right? The leader is going to go, or the protocol is going to go back to the initial configuration again and again and again. And then what it means is that by reversibility, it will eventually hit the right path, taking it from yellow, from red to green. Okay, so you know that by reversibility, this is the essential thing here, it's probably very, very unlikely. It takes a lot of time until it happens, but eventually it happens with probability. And well, then what you can do is just in order to obtain the protocol which really computes, you add a little gadget. You add a little gadget which adds transitions that whenever there is an agent that reaches this state grid, whenever the leader reaches this state, it attracts all other agents to this same state. Okay? And then what happens is that eventually it will be the case that the leader reaches this and empties all the others, it attracts all the others to this state, and then the protocol cannot do anything more. Okay, it will stay in that configuration forever. And it will be and then by making this the only thumbs up state, it happens that you are going to reach this thumbs up state with probability 1 if and only if the initial number of ninjas is at least 2 to the 2 to the. Okay? Good. So if there are at least this number of ninjas, the leader eventually reaches this state with probability 1 and attracts everyone to this. Notice that very often it will happen that it reaches this and it attracts some but not all, and then the protocol continues, but they will return, the ninjas will return to their states, and then it will take a lot of time until you reach this, and the leader is able to grab all the ninjas to its state before they do something else, right? But it will eventually happen.
Sorry, Javier, so you said that the length of a path is doubly exponential, right? So the agent somehow count the length of the path?
No, the idea is that every transition in the path extracts one ninja from this repository, from this state where they are. Okay. Good. Okay. So this is the point. We have reached the point at which I thought, okay, until now, I hope that everybody has understood everything. And now Philip told me we want to see a real proof. So now I'm going to give you a real proof. And then I will lose, I don't know how many of you, right? But, well, that's right.
I have a question. Javier, I have a question to the protocol. With this, right? So you used VAS with states, right?
Sorry?
You have used VAS with states. And
yes.
then the leader appeared out of it.
Yeah, but that's, well, you know, that's...
Is the leader necessary? That's the question.
Sorry?
Is the leader necessary?
Excellent question. The leader is not necessary, but that's one proof that is so complicated that I will not bring it up to you. In fact, you know, sorry.
Can you just use VAS without states and get a leaderless protocol? Is more complicated.
Yeah. Yes. And in fact, the question is right on spot, because there are 4 questions that you can ask. Because there are 2 models. Population protocols with leaders, population protocols without leaders, leaderless population protocols. These are 2 different models. And for each of them, you can ask the question, which is the lower and an upper bound on the constant C that I can reach with so and so many states. Okay? So there are 4 questions to be answered. This is the answer to the simplest answer to one of the 4 questions. I mean, simple once you know the result by Meyer and Mayer. I am going to give you a proof of a second one, the next one, which is easy, and when I touch this, apparently everything. And then the other 2, for the other 2, I'm going to wave my hands. The final result, let me anticipate it, is going to be that the final answers are the same for protocols with or without leaders. So this means the presence of a leader doesn't make a difference, although, of course, the lower bound for protocols with leaders is harder to obtain than the lower bound for protocols without leaders, and the upper bound, for protocols without leaders is harder to obtain than the upper bound for protocols with leaders.
So what is wrong with the following simplistic thinking, like that protocol with leaders is like VAS with states, and protocol without leaders is VAS without states? And then VAS with states and without states is very
well, no, but the important thing is which is the mapping going from configurations to from inputs to configurations in the bus, right? I mean, it's not, if you are thinking always of the time, okay, whenever I have an input, I am going to only put the, I'm only going to have a set of initial states, and all only those states will be initially populated, apart from the, then it's fine. What happens is that, in practice, you have protocols where you need 5 leaders in this state and 2 leaders in that other state initially. Of course, you can replace all that by having a sufficiently large number of vector additions with states. It's just a matter of only of definition. There is nothing behind it. So if you want, you can keep that.
Okay, so actually maybe there's one more thing you can say here. So like leaderless is like a VAS and like VAS with 1S, and you have to start with the 0 configuration.
Yes.
Yeah.
So that's so if you try to simulate VASs with states with VASs without states, you have to still start with a non-zero configuration. In a leaderless protocol, you're not allowed to do this. You have to start with the 0 configuration.
Okay.
Yeah. Okay. Then you can think, okay, so if in the end it doesn't make a difference, why are we discussing leaders? Well, first, the guys in distributed computing care a lot about leaders, because they also care about how easy it is to do the protocol, and sometimes it's much easier to do it with leaders. But it also does make a difference. There is a very surprising result telling you if you have protocols without leaders, this concerns speed. If you consider protocols without leaders, then you can show that for some predicates you need at least linear time. Okay? No protocol goes faster than that. And you would say, linear time, who cares, right? Well, you do care, because it's linear time in the number of agents. And when you have 2 to the 60 agents, linear time can be a lot of time. Okay, so in fact, what happens is if you allow a leader, then you can do it in polylog time. So the presence of a leader makes it possible to achieve exponentially faster protocols. So, and the guys in population protocols, they do care about speed, right? Good. Okay. More questions?
A question?
Yeah.
In polylog time.
Actually, you should continue asking questions, and then we reach the break. And
in polylog time, you can't even interact with all the agents. Right?
Sorry?
In polylog time, there cannot even be interactions with all the agents.
Okay, so that's a very good point. And then I was hiding things under the carpet. What is polynomial? How do you define time? Well, because if you are looking at Markov chains, then you say one interaction is one time unit. But of course, that's not how it works in chemistry. In chemistry, all those interactions are happening in parallel. And the question is, how do you connect number of interactions with time? And that depends on the model that you choose. You have to choose a model, right? And the model that is typically used is to assume that, you think you can visualize it like this. We are the agents, and there is a channel between any 2 of us, right? And the idea is that we are going to interact through that private channel following a Poisson process. So the idea is that we are going to interact 5 times per second in average, right? But the distribution is a Poisson distribution. If you assume that, so this means, as you know, Poisson distribution means intuitively there is no preferred moment in an interaction. All moments have the same probability. Now, under that model, which is reasonable, if you do the math, then it turns out that the time is, the average time is the number of executions divided by the number of agents. Okay? So, for example, then this means that immediately this means you are interested in protocols where the average number of steps in the Markov chain to the consensus, to the stable consensus, is n times polylog. Because when you divide by n, this becomes polylog. Okay? So that's your goal. You are interested in having protocols where the average number of steps to a bottom strongly connected component is n polylog, where n is the number of agents. There was some other question? No? Okay. So then let's since we still have 10 minutes, let me start with the proof, right? And then all of you who do not want to listen to a hard proof, you just have an extended coffee break. Good. Okay, so the goal is going to be to find a function f such that every leaderless protocol for x greater than or equal to c has at least f of c states. So we want to find how far, we say, we want to find, okay, we cannot go farther than this. Maybe we can go to log, 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 but we cannot go farther, or maybe we stay at log, log, and it's not possible to go farther, okay? Good, we are going to do this reversal thing. The idea is we're going to find a function g such that if some protocol with at most n states decides x bigger than or equal to c for some c, then c is less than g of n, right? So the idea is I give you a budget of n states, and the idea is you can only go up to g of n with that budget, okay? Good, so that's what we are going to search for this g of n. And the first thing, this one is easy, right? Which is but this is an important point, which is the proof technique the proof principle that you use? Well, you search for two numbers, a and b, okay? Such that every input of this form, a plus lambda b, for lambda in a natural number, gives you the same output, okay? For all those inputs, the answer of the protocol is always thumbs up, or is always thumbs down. But in fact, if you have found the numbers, then you know that necessarily C is less than A, right? Because the protocol decides, goes thumbs down up to a point, and then from that moment on, thumbs up, right? So these are the natural numbers, and the protocol is computing the predicate x bigger than or equal to C. So this means it initially, for all these inputs, it answers no, and from some point, it answers up, it answers yes. And now you have to place all these numbers, a plus b, a plus 2b, a plus 3b, here, but you have to place them either here or here, and there are infinitely many, so you have to place them here, okay? So this means that if C is here, then A has to be somewhere. Good, so this is the proof principle, yeah?
So is this linear dependencies kind of taken out of the space? It was like the idea of the space, or is there something behind it, like some reasoning why you choose this property that you want to have a plus lambda times b and not some other function that's growing?
No, it's just what happens to me.
Okay.
So it's just.
Well, so you can imagine it like pumping runs in a bus. So the idea is you want to find some run that you can pump.
Yeah.
The pump is called B, and the
And
run is called A.
Okay.
Yeah, the pumping could be non-linear, but you start with the easiest thing, right? Okay, so then remember the configuration is a stable consensus. If all agents have the same opinion, and the same holds for every configuration reachable from the configuration. And let's keep this in mind because it's going to show up a lot. This is the set of all stable configurations. Okay? Good. And then the first observation is very simple. So, in fact, you have already guessed it, right? The protocol is going to output thumbs up for some input A, if and only if it can reach a stable up consensus, the yes consensus. Okay, because by hypothesis, we have a protocol which computes a predicate. So it means if for the input A, we have the corresponding initial configuration, the initial configuration of A, if we can reach some stable consensus, this is this configuration, then the Markov chain from here, it can have different n components, but this is going to be, well, in fact, it could also be here, but the idea is that all these consensuses here, they have to be of the same kind. Okay, so.
And must be consensuses, right?
And they must be consensuses, yeah. Okay, so everybody happy? Okay. So this is the first observation. And now this is the second observation, which is the first one, which is a little bit more technical. Okay, first, the set of stable configurations is downward closed. Well, why? Imagine that you have a configuration which is a stable consensus. So this means that anything you can reach are stable consensuses. Okay? Good. Now imagine that you have a smaller configuration you obtain by removing some agents. Well, then if from the larger configuration you cannot reach any, you cannot put a token in any state of the opposite opinion, then you can also not do it from the smaller configuration. Okay? So everybody got that first part. Okay, so it's downward close. Then this means, well, so then a little bit of something that probably almost everybody, or probably everybody still knows here. You know, downward close means that if a configuration is in the set, every smaller configuration is in the set. You know, there is also the notion of upward close. If a configuration is in the set, every larger configuration is in the set. You should all be familiar with Dixon's lemma. Any upward close set has a finite set of smallest configurations. Maybe you are familiar with the kind of opposite, which says that every downward close set has a finite set of maximal configurations, where you have to be explicit about what that means. Because now the idea is that a maximal configuration, you generalize the notion by saying a maximal configuration is you allow to have omegas in some components. So you can say, I consider a configuration of the form 2 tokens here, 5 tokens here, and an arbitrary number of tokens here and there. Okay, is everybody happy with that? Well, okay, so if everybody is happy with that, we are going well. Because then you understand this second line. Then the set of, this gives you a structure to the set of stable consensuses. You can decompose it into a finite number of basis sets, which are of this form. And you should also remember this form. This is a configuration. And this is a set of states, or for those thinking in terms of basis counters, right? And these are the counters where there is no bound on the number, okay? So you have a finite number of those. Good. And this is the third fact is also very simple. Once you take one of those sets, then all the configurations there have to be either thumbs up or they have to be thumbs down. You cannot have a mixture of the two in the same set. And that's very easy because, you know, whether it's thumbs up or thumbs down depends only on the support of the sets, not on the number of elements. Everybody following? More notes? I need more notes.
So
I see some.
Depends on the support of, what do you mean by support of a set?
The support is only also the set of states that are populated that have at least one agent. Okay? Okay, so let's see. So you describe a configuration as a vector, right? And then these states are either thumbs up or thumbs down. If this is a consensus, for example, then this means that all these states, they have to be thumbs up, say. Okay? The thumbs down, they would have to be here. Okay? And so if you now take a larger configuration where you keep these two at 0, then they will still be in the same consensus. Okay, everybody happy now? Good. Now the last one is the one that is more tricky. You can put a bound on the size of B. So you can say that the B is going to be, for each of these sets, at most double exponential in n. And this is a consequence of another fact that probably many of you know. That's the Rakow's theorem. Okay? Rakow's theorem tells you that if you can reach a configuration with some support, or which puts a token somewhere in some specific state, then you can reach it by means of a sequence which has at most double exponential size. Okay? And that's why you do not, I mean, if that's why you only need the double exponential. So let me see which is the connection between the two. I have to work it out now.
The numbers that appear are at most double exponential.
Yes.
And then
But it doesn't
find
look
the
at.
number of coordinates.
Sorry?
And the number of coordinates is like.
The number of coordinates is n, because, sorry, not n, sorry, it's the number of agents, right? And, oh, I am, sorry, no, n is the number of coordinates, sorry, yeah. N is the number, the dimension of the vector, the number of states. Sorry, I am, forget about, n is the number, the dimension of the vectors, right? And then, why do, so if there would be, if they would be larger, well, the idea is always, yes, so it's just, right, okay, so the idea is that you have the set, the upward closed set of the complement of the consensuses. So these are the configurations from which are not a stable consensus. That set is upward closed. For that set, you can find a minimal set of elements, right? And the components in those minimal elements, they are going to be at most double exponential, because if something is not a stable consensus, this means that it is possible to reach a configuration where you have tokens in states of a different kind. If you can reach a configuration with tokens in states of a different kind, you can reach it by means of a sequence which is at most double exponential. Okay? So the smallest configurations which are not stable consensuses, they are always going to be at most double exponentials. And then this tells you that the components in the minimal elements of the upward closed set are going to be double exponential, and when you take the complement, you are going to see exactly those numbers again, or at least those are, you're going to see numbers which are taken out of those. Okay, so at least Georg is nodding all the time. Keep on. Keep the good work. Okay. Good moment for a break. Yeah. So let's stop here, and let me give you the program for the next, let's say, half an hour or so. We will have a warm up. We will find the first argument, very simple, proving that we can have an Ackermann bound, upper bound on C, and this will be something easy. And then we will have the real thing. And we will see that we can find the double exponential upper. And that will be a bit more tricky. Okay? Good. That's it. Thank you.
Thanks.